So, so as I said before, we're going to use GitHub. So we have the exercises are at GitHub. So the slides, I'm updating it. I will also put today Mandes's slides. Up there is the page, github.com. So there you can also view the slides. And are you familiar with Git? Have you worked? Okay. So first, what you have to do is log in into your account at Pittsdane, this courses XX account. Git clone this thing. You can copy the link also either from the slide or well, I have not yet put the slide on. I should put it. But if you go to the page, there is a clone button on the top right, and you can get this exact link. So there you will see basically 3 directories. It's the exercises, and there we have a subdirectory called Cray, which are the exams Mondays will present in the first 2 sessions tomorrow that we'll work on. And then there is an OpenACC directory, where are the several exams of OpenACC. We're going to work on 2 of those examples. And then there is a directory solutions. Now it's, well, it's not there actually. It will appear there after the course. And the slides is where we have the course. So meanwhile, though, we may find that something is buggy in the exams or compiler, or I mean, something doesn't compile or whatever. So I may need to do some changes. So this is the command that you should do in order to get the latest version. So git pull origin master and you get the latest version. For example, the fake files in case something has slipped my attention. Well, these are the exercises. So yeah, tomorrow Bandes will present more about the Himeno exercises, the Himeno benchmark, where you're going to see the basic concepts of directives, and we're going to incrementally start from a less optimized and go through a more optimized version. Then we have 2 other examples. One is, basically it's a 2D diffusion example, which actually combines MPI with OpenACC, and there is also a version that you can compile and use with CUDA, so that you do your data management in CUDA, and then you just use those CUDA pointers from within OpenACC. So you can see the interoperability. And finally, I've prepared a simple gem example that starts with a naive gem implementation, like out of the textbook, that takes ages to run. Then there's the loop reorder version, and then we ask you to port that to OpenACC, and then instead of writing your own gem, why not using kublas? And this is, yeah, basically we'll ask you to put the correct directive so as to call kublas and run some measurements. Well, in the last 2 exercises, there's a to-do tag that you can search for in order to find the places where you should place your OpenACC directives. So, well, I'm not going to go through now to all this because I'm going to present this tomorrow more specifically. Do we have? Not yet. So what I can show you then, currently we have a problem with the reservation. So I don't know if somebody of you tried to submit like a trivial job.
Huh? It's not the reservation, it's one user. Yeah. There are lots of tiny one-node jobs.
Oh, okay, and it's hanging the whole machine. Okay, it's the same. Yeah, it's unrelated then to preservation. So it's. So meanwhile, Mandes has shown you how you get this useful information. What blocks are what loops are blocked, or which loops are vectorized, or how they are transferred to the GPU. I'm going to show you a bit how this happens with a PGI compiler. So I'm gonna now get into my account. Well, I don't need to submit a job for that, so okay, tell me if, okay. So, well, I'm going into the solution that we'll get later, but since here are the directives, so this is the diffusion example, so I'm gonna clean it. Okay, so you see some information getting printed here. Okay, let it compile, and then I'm gonna show you what those things mean. So, okay, let me go a bit up. So there, Fortran and C++ version, everything is compiled, but let's have a look here. For example, at the top you see, before that I want the compilation command. Okay, so you see up there an minfo accel. So minfo is the option that you ask the compiler to print info about what is doing. So this would just say, okay, print some info only for the what is related to the accelerator. So here you see that, okay, in the specific file, line 17, okay, I'm generating a present, what array. So you can go into your code and see if that's generated exactly. Then you see the loops, how they're generated, and you see also this block idx.x, thread idx.x. These are actually CUDA, so you can correlate with how the CUDA code would look like. I mean, how large are the blocks, the grids, etc. Then let's see. Okay, then you see a create. So this is either an ACC create or it was just a copy in. So it first creates and then also generates a copy in or copy out. So this, you can see also what the compiler exactly does. And sometimes you may not be so explicit. For example, your code, you may not have pragma ACC loop gang vector 108-28 collapse. You may just have ACC loop, and then the compiler makes some assumptions, and this is how you see exactly what it has generated and understood. So, well, this is more or less the information you get. You can increase your level. So if I go into the make file instead of accel, I say all, I will get all the info. Okay, now let's be prepared to get okay, now we're getting lots of info about inline function. Yeah, it's lots of output. So that's why by default I have it only minfo accel. Okay, we get also from the basic string what has, yeah, I really recommend against using a minfo unless you really want to see what's going on, because the output is really a lot. But I could probably put not here. Yeah, in the Fortran. The Fortran would be probably the Fortran version. So here let's just put accel and Okay, let's see. Okay, for the C++ version, we just get what we expected. Let's see also for the Fortran version. Okay, so you see, for example, the loop at line 70 was unrolled 4 times. And okay, so if, for example, here, line 11, you can see that it detected an idiom of memory copy, and it replaced that with an optimized memory copy and all this stuff. But this is only if you're interested in exactly what's going on. Usually, we just use the minfo to understand and be sure that the actual code was generated. So, and another thing that probably due to this problem we have, I cannot demonstrate it right now, is when you run, you can also get some runtime information if you have compiled with a PGI compiler. And if you export the variable, it's PGI ACC notify. Okay, so if you do this, and then you set a level, so 1, 2, I don't know if there's 3, and then you will get runtime information like now I'm launching the kernel, now I'm copying, now I'm all these things. So you can track probably some bugs. You can try all these things during the hands-on to get a feeling of them. And well, now, ideally, I'd like to okay, let me just check if we can submit a job. Unfortunately, there's a user.
If you go to Slack, you can show.
I can log into DOM,
Yeah.
right? Yeah. DOM works. Okay. Yeah. So. Okay, so now. Okay. And the module load CUDA toolkit. So now I'm gonna demonstrate the use of NVProf. Okay. So here's the GPU, not debug, and NVProf. Okay, let's see.
I have a really stupid question. So the question is, you have TA is equal to Tesla :CUDA 8.0.
Yes.
Is there anything different than Tesla :CC 60? That's what I'm using. Where do you, what is the right option?
Yeah, I haven't thought of it because.
I'll try that one too.
Okay. I think they're equivalent, but. Okay, so here is what you get as an output. So NVProf is the NVIDIA profiler. So you can use the same profiler also for CUDA codes. And here you see, okay. So you see that everything's basically translated into CUDA calls. And then you get a low-level breakdown of what's going on And here is, okay, some OpenACC related. So for example, here the enter data took the most of the time there at the gem CPP 63, line 63. And then you have the weight, the kernel, so you see, and then you can associate with what exactly gets generated from your OpenACC calls. Let me check if I have the -G. Okay. Yes, because I forgot this. Probably I should add it. So let's see if we have more. Debug information. Okay, yeah. You see also in Q launch, yeah, it launches the kernel, and you can also view these things visually. But let me see what has. Zizi, do you know I don't remember so as to get the binary output.
Dashboard. You will get a binary.
Okay. Okay, so this is basically the output of the program. This is the timings, taking result and stuff. So now we've got an nvprof.out, and I'm gonna open it with the NVIDIA Visual Profiler, so that you can have a nice view of what's going on. Okay, so let's see. Well, this is a small code, so I mean, in real application, you will see much more interesting, probably, results. So why doesn't? So here, for example, this is our kernel. Let me just resize the window. Come on. View. Okay, so here are the runtime calls. Here you see that you're running on a Tesla P100, and they're the data transfers. So memcpi hosted device to host. So you see that everything is translated to CUDA. And here's basically the compute. So here we have, yes, this is the open, let's see if it's, okay, just a minute. Why it can, okay, if I do it like that, okay. So, and then okay, there's filing overhead. So, well, this is a bit trivial example, but usually you can see also, here you have the kernels, and then, okay, here we have it. That's nice. So here on the right, you see exactly how much each kernel took. The start, the end, the duration, it was 20 milliseconds. You can see the exact CUDA streams that were generated. I mean, the grid size and the block size. So this is how, I mean, the number of threads you had in the block, the number of registers each thread uses, 48. Then you have and other metrics like the occupancy of the GPU. So with this configuration, you just get 62.5% of the GPU. And then you can, with your OpenACC directives, you can fine tune, for example, the number of gangs you want, the vector length, all these things. You can fine tune them and see how the performance goes. But you need a profiler to look at what exactly is getting generated, and you can see such metrics. Here, okay. You can also, okay. So you have here, come on. Yeah, sorry, the screen is a bit. Okay, so here we have perform kernel analysis. So okay, probably I have missed an option here. Sorry for that. Okay, you see also the shared memory request and all these things. Probably we should. I can retry with more options. Okay. Okay, let's try this. Oh, come on. Okay. So there we're going to get several metrics, and that's quite useful because you can get into the details. Okay, let's see now how the output looks like. And usually, in order to get, this is similar with several tools that they use hardware counters on the CPUs. Those programs usually rerun the same executable several times because there are usually hardware limitations on the number of performance events you can collect. So let's see again. Okay, just a minute because I don't know why it hasn't a full screen thing. Okay, let me pick a kernel. That one. Okay. Okay, and then I'm gonna perform perform kernel analysis. Okay, so now you see kernel performance is bound by instruction and memory latency. And so here you see several interesting measures. I'm not gonna go through them each one individually, but we can discuss it for different kernels later. So you see also here this one. For example, you have a theoretical occupancy of 62.5%, and you get 60.7. That's because some warps diverge, so you don't get the full. Okay, we can. let's see the utilization function unit. So yeah, this is a gem kernel. So expect it, it's an unoptimized one. So we are bound by instruction with memory latency. So let's see also perform latency. Perform memory bandwidth analysis. That's probably easier to grab. So you see, doesn't have enough requirements for memory bandwidth. You can see all the metrics basically here. That's really, it really can help you with your code. So compute bandwidth, okay, perform compute analysis. Let's see if we have. Okay, that's a bit low level. If you really want to dive into, okay. Let's see the whole report here. Okay, we see here we have several integer, and probably we're doing some, it spent some time going through the loops, the loop overhead, so it's not optimized at all. Okay. Come on. So this is how it looks like. I mean, I have not prepared an example to go step by step on the optimization. So I'm just showing you for the moment that it's a really helpful tool that you can see exactly the details, go into, I mean, at the very low level and understand what's going on. So then you can tune your kernel, you can tune your access patterns to get more performance. Yes?
Could I use the same tool when I would run OpenMP? Would that also have then CUDA as a backend and then?
I haven't tried it, but in theory, I suppose yes. Haven't tried it. Yeah, and we tried it during the hands-on. Yeah. Reservation bug. Yeah, but still, I mean, I showed what I wanted. So, so yes, I mean, now for the moment, I encourage you, I mean, clone the repository, familiarize a bit, just running srun for the, I mean, to see how you get a note the reservation is back, and just familiarize for the next 10 minutes, and then we're going for the visit. Okay, so, and another final thing about the examples. The example, they should compile even without the directives. So if you do make, for example, for the, at least for the diffusion and the gem example, what's in the exercise, it should compile, but of course there are no directives, so if you try to run, you will get errors, so the results do not match, etc. But about the details, we're gonna talk tomorrow for the hands-on. First, we're gonna do the Himeno and then the other exercises. So yes, that's it. So, so as I said before, we're going to use GitHub. So we have the exercises are at GitHub. So the slides, I'm updating it. I will also put today Mandas's slides. Up there is the page, github.com. So there you can also view the slides. And are you familiar with Git? Have you worked? Okay. So first, what you have to do is log into your account at Pittsdane, this courses XX account, git clone this thing, you can copy the link also either from the slide or there's a to-do tag that you can search for in order to find the places where you should place your OpenACC directives. So, well, I'm not going to go through now to all this because I'm going to present this tomorrow more specifically. Do we have? Not yet. So what I can show you then, currently we have a problem with the reservation. So I don't know if somebody of you tried to submit like a trivial job. Huh? Oh, okay, and it's hanging the whole machine. Okay, it's the same. Yeah, it's unrelated then to preservation. So it's. So meanwhile, Mondays. I have not yet put the slide on. I should put it. But if you go to the page, there is a clone button on the top right, and you can get this exact link. So there you will see basically 3 directories. It's the exercises. And there we have a subdirectory called Cray, which are the exams Mondays will present in the first 2 sessions tomorrow that we'll work on. And then there is an OpenACC directory where are the several exams of OpenACC. We're going to work on 2 of those examples. And then there is a directory solutions. Now it's, well, it's not there actually. It will appear there after the course. And the slides is where we have the course. So meanwhile, though, we may find that something is buggy in the exams or a compiler, or I mean, something doesn't compile or whatever. So I can compile and use with CUDA so that you do your data management in CUDA and then you just use those CUDA pointers from within OpenACC. So you can see the interoperability. And finally, I've prepared a simple gem example that starts with a naive gem implementation, like out of the textbook that takes ages to run. Then there's the loop reorder version, and then we ask you to port that to OpenACC, and then instead of writing your own gem, why not using kublas? And this is, yeah, basically we'll ask you to put the correct directive so as to call kublas and run some measurements. Well, in the last 2 exercises, you may need to do some changes. So this is the command that you should do in order to get the latest version. So git pull origin master and you get the latest version. For example, the fake files in case something has slipped my attention. Well, these are the exercises. So yeah, tomorrow Bandes will present more about the Jimeno exercises, the Jimeno benchmark, where you're going to see the basic concepts of directives, and we're going to incrementally start from a less optimized and go through a more optimized version. Then we have 2 other examples. One is, basically it's a 2D diffusion example, which actually combines MPI with OpenACC, and there is also a version that you can